Hi, we're going to cover general theory for linear differential equations. Uh, the mapping D that takes you from C1i to C0i, where D stands for derivatives of f equals f prime, is a linear transformation. D is called the derivative operator. Higher order derivatives will look like this: d to the power k. That means d times d times d derivatives up to k times, or will be d times d to the power k minus 1. So if this is 7, this would be like d, one more, of d to the power 6. Those are just like notations for derivatives like higher order. We know them. We're going from ck I to c0 I. ck is a set of all continuous functions with at least k continuous derivatives on I. Example: if L is written as d to the second plus 4x d minus 3x, then what's Ly? Second derivative of y will be y double prime. 4x times derivative of y will be y prime, and minus 3x times y will be y. There is no derivative here, so there is a y. If you need more details, I have it coming right here. Let's call L y with two different colors. L, which is derivatives or linear transformation operator on y. It's kind of like distributive property, or you're multiplying this L, which is d squared plus 4x d minus 3x multiplied by y. So y d squared, that's the second derivative of y, which is d squared times y, and 4x d multiplied by y minus 3x times y. Derivative right here will be y double prime. Derivative of y will be y prime. No derivative right here, and it keeps it like minus 3x y. Okay? Next. Here's an example. If y equals sine x, and you want to apply this operator on it, you need the second derivative of sine. We go sine, cosine, then we come back to minus sine. Minus sine x squared. For x times y prime, derivative of sine is cosine, minus 3x times y by itself, right here. If y equals x to the second derivative will be 2, because you go from x to the second to 2x, then to 2, and second term will be 4x times y prime. Y prime is 2x times 4x will be 8x squared. Then the last term will be minus 3x times y, which is x squared. Okay? By taking a linear combination of the basic derivative operators, we obtain the general linear differential operator of order n. L equals d to the power n, that's nth derivative, plus a sub 1 d to the power n minus 1, 1 less, all the way down to a sub 1, defined by Ly equals y to the power n, which is nth derivative of y, all the way down. Now, this section is a general theory for linear differential equations. Notice, as they're saying right here, a sub I, they're functions of x. On the coming section, we're focused on constant coefficients. So those a sub I will be constants. Let's going from c to the power ni, which was described earlier, to c sub 0 I, c to the power 0 I, is a linear transformation, meaning the transformation of the sum is the sum of the transformation. That's number one. Number two, the transformation of a constant or a scalar multiplied by your function or vector will be a constant multiplied by the linear transformation of that y1 for all y1, y2 in C and I, and all scalars C. Homogeneous linear differential equations. What's homogeneous and what's not homogeneous? Homogeneous when you have everything written to you and equals to a 0 on the right side. We first consider the nth order linear homogeneous differential equation. It's kind of lengthy to read, so I have it for you. Notice on the right hand side we have 0. We describe this by homogeneous. Defined on an interval I. The differential equation can be written as the operator equation. Ly equals 0. We're still in homogeneous. And we're going from C ni to C 0I. It's the nth order linear differential operator. L equals d to the power n plus a1 d a minus 1. D stands for derivatives or derivative operator. If we let S represent the set of all solutions to the differential equation, and now we have the linear combination of those solutions. Now then, S will be all the y that belongs to C and I such that Ly takes you to 0. But this has a short name. So if you're solving a system of linear differential equations of this type, meaning homogeneous, so homogeneous system, your output is 0. And if your output is 0, the set of solutions will be called the kernel. That is the kernel. Here's an example. Determine all solutions to the differential equation y double prime minus 2y prime minus 15y equals 0. Of the form, they're telling you how they look like. These equations, they have solutions that they always look like y of x equals e to the power rx, where r is a constant. Use your solutions to determine the general solution to the differential equation. Let's go step by step. If y equals e to the rx, the way they are telling me right here is a solution, y prime is r e to the rx. And finding the derivative again, r will go down again one more time. This becomes r to the second, as you could see right here. Now we have them. Let's go back to the original equation and plug them in. This is a step-by-step process. Later on, we're going to be skipping those steps. So we have y double prime minus 2y prime minus 15y equals 0. But what is y? E to the rx. And what is y prime? R e to the rx. And what is y double prime? R to the second e to the rx. One by one, we're gonna plug them in. Here's the first one, goes in front of, or like for the 15, minus 15 e to the rx. Here's the second one. For y prime, we're gonna write r e to the rx. For y double prime, we're gonna write r to the second e to the rx. Let's write them down as an equation. Alright? Notice they all have e to the rx. So we could pull e to the rx from the right as a common factor. We end up with what's left inside, r to the second minus 2r minus 15. 15 could be factored to 5 times 3. More negatives will give the 5 a negative sign. And now I have two solutions. When you set this equal to 0, after you factor it, we get r equals negative 3 and we get r equals 5. That doesn't give me 0. It doesn't touch the x-axis. It's an exponential function. Alright? So we have two answers. Either r1 equals negative 3 or r2 equals 5. And note that e to the rx does not give you a 0. We have two solutions to the differential equations, which are y1 of x equals e to the power minus 3x. Remember this form right here? We found r1, so we put it up there for r, and this is minus 3x. We do the same for r2 equals 5. We get y2x equals e to the power 5x. After that, they told me to find the general solution. Determine all solutions. We did that. Now use your solutions to determine the general solution. Now, before we move on, don't want to forget this comment. If we do the Wronskian for these two functions, we end up with 8 e to the power 2x, which is not equal to 0. That means y1 and y2, those in red right here, this one and this one, are linearly independent on any interval. Let's summarize this problem in short. So we started with this. They told me how the solutions will look like. I took advantage and I did the derivative, and the second derivative went back in, and this right here, later on we're gonna skip those steps. Notice that this right here, y double prime minus 2y prime minus 15y it looks like this. Second minus 2 times minus 15, just for later on. But let's move on to this problem and stay focused on these two solutions and the general solution, which is going to be combined, a linear combination. A basis for the set of all solutions to the differential equation is e to the power minus 3x and e to the power 5x. So the general solution to the differential equation is the linear combination of these two. Y of x, which is called GS, or the general solution, is c1 e to the power minus 3x plus c2 e to the power 5x. Okay? Theorem. If we have those as solutions, y1, y2, y3 up to yn, be linearly independent to Ly equals 0, which is the homogeneous, on an interval I, we let y equals yp be any particular solution to Ly equals f. This is the homogeneous If we have something on the right side like capital F, with that in mind, we found something else. It's called the particular solution for this right here. Will fit right there. Now we're gonna talk about the general solution for what's happening. Earlier we had this only. Now we're coming with a new non-homogeneous system, knowing that this has a solution as particular. Then every solution to Ly equals F on I is of the form y equals C1 y1 plus C2 y2 up to Cn yn plus yp. This is for the homogeneous. Earlier example we had two y's and we did C1 and C2 to combine them. That is for the homogeneous. For the non-homogeneous, if there is a particular solution, we call it yp, combining these two will get the general solution for the non-homogeneous. Here's a comment that I want you to keep in mind. This in red is for the homogeneous, and we use C1, C2 up to Cn. That's how we do the linear combination. This one does not have a C. I know some students they add a C to it. No, it's just yp by itself. Okay? According to the theorem, the general solution to the non-homogeneous differential equation Ly equals F excuse me, is of the form yx equals yc of x plus yp of x. I'm using different colors to keep you focused. Yc comes from the homogeneous and yp was added when we had the non-homogeneous, where yc equals c1 y1 plus c2 y2 all the way to cn yn is the general solution to the associated homogeneous system or equation Ly equals 0. And yp is the particular solution to Ly equals F. We refer to yc as a complementary function of Ly equals F. Probably that's why they use the letter C right here. We refer to it as the complementary for Ly equals F. So kind of like if you are given Ly equals F, you treat it first as a homogeneous, then you find that solution or general solution, which is yc, and that becomes a complementary to this non-homogeneous after you make it homogeneous. Example. Verify that yp equals 2e to the power 2x is a particular solution to the differential equation given below. Y double prime minus 2y prime minus 15y equals 18e to the power 6x. And determine the general solution. From the previous example, we found the general solution to the homogeneous Ly equals 0 to be yc equal, I'm going to call it yc now, c1 e to the power minus 3x and c2 e to the power 5x. Now, they're not asking me here to discuss all these steps and verify that those are solutions to the non-homogeneous, or the homogeneous, I mean. When this is 0, that's called homogeneous, but I'm doing it to show you the steps. So let's go for some steps to show you more details. So if we check if y1 equals y1 equals e to the power negative 3x is a solution to the homogeneous Ly equals 0, we just take y1, put it right there, take y1 prime, which is negative 3 e to the negative 3x, put it right there, take y1 double prime, which is going to be a positive 9, e to the power negative 3x in the front. When you reduce and simplify, you get 9 e to the minus 3x plus 6 minus 15. They're all the same. E to the minus 3x, e to the minus 3x, e to the minus 3x. But 9 and 6 is 15, minus 15 is 0. So yes, this will work. It's part of the solution. It's a solution to this right here with the 0 on the right side, which is called the homogeneous. Same idea, we could test for e to the 5x. But we're going to move on and skip the steps. Likewise, you can check if y2 equals e to the power 5x is a solution to ly equals 0. Now, however, we have now the non-homogeneous differential equation. It's non-homogeneous. So this is in our way 18 e to the power 6x. And yp equals 2 e to the 6x. Now, they did not tell me how to find it, at least for now in this section. If you go back, it says verify. So they gave it to me. They gave me yp, but they're not telling me how to find it if I'm on my own. So we have now the non-homogeneous, which means we have on the right side the 18 e to the power 6x. To verify, I'm going to do the following. Yp equals yp prime equals yp double prime equals 6 goes up front, this becomes 12. 6 goes up front one more time, and that becomes 72. We go back and plug them in one by one. Let's go. This is the left hand side. Plug in y double prime. Notice that we're verifying now. We are using yp. This is yp. This is also yp. The second derivative, the first derivative, and the original yp, which is 2 e to the power 6x. Okay, we're gonna plug them in and try to simplify step by step. I have the following. Notice they all have e to the power 6x, which is gonna be getting out as a common factor. That's after you reduce. E to the power 6x is a common factor outside. 72 minus 24 minus 30 is 18. You could do the math and double check. But that is what they want. So we started on the left hand side. We used 2 e to the 6x that they gave me, that this is a solution to the non-homogeneous, meaning if you plug it in to test it, you're gonna get a right hand side of the value of 18 e to the 6x, which we did. And that's the right hand side. Now, we're almost done, guys. I mean, this section is all about telling you the homogeneous and the non-homogeneous, the particular YC, the particular YP, and the complementary YC, and how we could combine them. So that's it for 8.1. If I have a chance, I'm gonna upload 8.2 today. I have the notes ready. I just finished 2 videos today, and I'm working on the 3rd one. Thank you for watching. Consider subscribing if you do like it, and comment below if you have any comments, and I'll get back to you as soon as I can. I always check my comments. Until next time, peace. JaberTime.